All right, so we are live. So welcome everyone and happy Space Week. It's our last day of Space Week. My name is Lucia and I'm your host. I am broadcasting live from Oakville, Ontario, so that's why I recognize that Canada 150 flag. All week long we've been having Google Hangouts with astronauts, engineers, astrophysicists, roboticists, scientists, just so many other people who love to explore outer space. So thank you for joining us today. And remember, any photos that you take during our Hangout, you can actually share them online with the hashtag #ExploreSpace, because at the end of the week, so sometimes today, we're going to choose some classes that are going to win an awesome National Geographic Space Prize. So today we have classes joining us all across Canada and America. So we have class from Freehold, New Jersey, from Kitskote, Alberta, from Richmond Hill, Ontario, and from Ottawa, Ontario. We're still waiting for 2 more from Georgia and from New York, so hopefully they'll join us in a bit. And today we are hanging out with Dr. Stefanie Milam. So she is a planetary scientist that uses radio telescopes all over the world to observe comets and what they're hitting, but she's also on the team for the James Webb Telescope, which is a big telescope that's being launched in 2019. And it's going to help us observe the universe in a way that we've never had the chance to observe it before. So I'm going to pass it off to you, Stefanie. You can take it away.
Great. Thank you so much. Hi, everybody. My name is Stefanie, and I work at NASA. I work at NASA just outside of Washington, D.C. So it's one of our major research centers. It's called the Goddard Space Flight Center, which actually is the place that is doing a lot of the construction for the James Webb Space Telescope, but also a place that has a lot of research going on. And I'm going to give you a little bit of insight into what I do and how I came to be what I am today. So how I got to be a NASA scientist. So let me share my presentation with you. Okay, so I am actually one of the project scientists. So I'm a deputy project scientist, and I'm one of the only project scientists that actually has a very specific science designation. So I was assigned to the James Webb Space Telescope to be the planetary scientist. I'll tell you why I have this distinct role and why we needed this for the project in a little bit, but I just wanted you to know who I am and what my title was. But I didn't always have a title. I did start out in school just as you did. I was a very ambitious young girl with really big dreams. When I was 6 years old, I told my mother I was either going to be an astronaut and work for NASA, or I was going to be a ballerina. I kind of came from a time when everybody saw me as a very feminine little girl. I did go to ballet every day, and I wore dresses. And at the time, it was sort of under the impression of, you know, I was too girly to be a scientist. But I never let that stand in my way. I always knew that I wanted to do something more than a typical job. I knew I wanted to be working for NASA in the space industry, and hopefully one day go to space. I also, I thought everybody went to college. I grew up in a fairly affluent area, so where people had a lot of education and good jobs, and I just assumed that everybody went to college and got a higher education. I was very good at math and science as a kid, so I knew that that was something that I would pursue throughout my life and my career. And I never let anybody tell me no. And I also, if I did something, I did it as best I could. I never slacked on anything. I always did all my homework. I always studied for tests. When I went to dance class, I tried to do my best and perform, even in just a classroom setting. So it's just the person that I am. I was always very driven, and I knew that I wanted something more. So my life actually took me into very different paths. So depending on, you know, what the given situation was. So for example, the space shuttle was something that I hoped to be working on when I was a child. But unfortunately, that mission no longer exists. We no longer have a space shuttle working. So whenever I came about to work at NASA, it was basically so that I could become a mission specialist, which is a scientist that flies on either the space shuttle or the space station. So how did I get here? Well, it took a lot of work. It took a lot of discipline. I had to really study. I had to work very hard. I'm not a genius by any sense, but I do work really hard and I study really hard. So it took a lot of discipline for me to get here. I'm also an opportunistic person. Every time I had an opportunity to meet somebody, so if a scientist came into town and was giving a talk at a local library, or even at a museum, or doing a public lecture anywhere else, I always tried to pursue an opportunity to, if anything, go and listen to them, but also, if I could, try to meet them. Because you never know who you're going to meet and what advice they may have, or maybe even connections. And the most disappointing part of how I got here was my sacrifice. This isn't true for everybody, but it was true for me. I could not get the education I needed to be the scientist that I am today back where I grew up. So I had to move away from all my friends and family to get a higher education. And that was something that I had to do. Even to this day, I don't live anywhere near my family, so I have to make a point to try and visit them as much as I can. But I finally made it. I finally got to NASA almost 8 years ago now. And the first thing that everybody always thinks of with NASA is usually astronauts or space exploration. But NASA does a lot more than just space exploration. So we actually have a whole area that's dedicated to aeronautics. So this can be everything with planes and jets, how we fly, air traffic control. So every time you get on an airplane, we have to supervise how planes are flying, where they're going. And this is something that you know, we actually have to work on and we have to study, because we don't have traffic lights or police working the skies. We do have human exploration. So this is our astronaut program. So this is working on the space station, conducting science experiments out there, monitoring the Earth, as well as other planets nearby. But we also work with the commercial spaceflight corporations hand in hand. This helps us actually a lot, basically advance our technology, but also financially. This allows for us to free up some of our funding that we get from the government to do other things besides just human spaceflight. We do science, a lot of science actually. We explore everything, including the Earth, the sun, the planets and small things in our solar system like comets, and all the way out to the beginning of time, as I'll talk about in a little bit. And we also develop technology for space. So this includes things like, how do you get a battery to operate in space and for a really long time? How do we communicate with satellites that are at the outer edges of the solar system? These are kinds of things that we really work on and need to be advanced. But today I'm going to focus a bit more on just science. But if you're interested in any of these other things, just feel free to ask questions whenever we get to that point. So as I said, NASA has a lot of science, and it's not just space. And we cover things like Earth science. So if you look down here, this is some imaging that we've done from space of the South Pole of Antarctica. And you can see what it's doing is monitoring how much ice is actually around the South Pole. So we can study these kinds of things from space. We also do astrophysics. So we're looking for evidence of black holes. We're looking how stars form, how they die. Are there planets being formed, and how? These are the kinds of questions we really want to know. We do planetary science. There's so much we don't even know in our own solar system. It's funny to think that we're exploring things outside of our solar system, but there's still questions that we don't even know inside our own solar system, including how many planets we actually do have. Right now we have 8, but we know there's a number of smaller planets in our solar system. And this is actually a really big deal for us because it tells us how our solar system actually formed. So we're still looking and still learning a lot about things in our own solar system. And then of course our own sun. This is the reason we're here. The sun provides all the energy that we need to live, for life to thrive, for plants to grow. We need sunlight. We need the warmth of the sun. Without our sun, we wouldn't exist. And we need to understand how the sun is going to evolve, how it's going to die, and other processes that happen that cause really cool things like, you know, aurora, or even how it affects things like gravity. So I want to go in a little bit today to how do we study things that are really far away. Since we can't necessarily get there, we have to do things, as we call it, remotely. So we have to look at things through telescopes. And we have to learn things by not actually going to something and picking up a scoop of dirt and studying what that dirt is made of, or sending a probe to another star. These are things that are outside of our capabilities right now. So we have to know how to study these things. And the way we do that is by looking at its spectra. So the electromagnetic spectrum is basically looking at light. But light isn't necessarily things like the sunlight, things that you see with your eye. That is something that actually operates at visible wavelengths. So that's what's right here in the middle. So this is why we see colors. This is why there's day and there's night. But light actually exists at other wavelengths. So you can go to longer wavelengths. So you can go out to regions where radiation actually exists in the form of radio waves or microwaves, just like your microwave in your kitchen. Or we can go to much shorter wavelengths out towards X-rays and gamma rays. So an X-ray, this is the same thing that actually gives you an X-ray when you go to the doctor if you break a bone. Spectroscopy is not only used in astronomy or even in a medical sense, but it's used all over and for almost every area of science. We use spectroscopy to study biology. We use spectroscopy to study chemistry of things. So it's an excellent tool to really understand what's going on. So in the context of NASA or studying things in space, we actually have to sometimes put telescopes in space in order to study given wavelengths. So if we want to study these high energy things, such as X-rays, for example, we're fortunate enough that a lot of that is actually protected from the Earth, from our Earth's atmosphere. So in order to really study it with extreme sensitivity, we actually need to go above the Earth's atmosphere. So we send out spacecraft to do so. And this is true also as we go into the ultraviolet and towards the visible wavelengths. A lot of light comes down to us in the ultraviolet. This is why you have to wear sunscreen, for example. But not all of it does, which is a good thing for us here on Earth, but it's a bad thing if we want to study that in space. Visible light, we can study from the Earth, but we're limited to whenever there is actually light that we can see. So for example, if it's daylight out, we can see everything on Earth, but we can't see anything in space because it's just, it's not bright enough to see through our own sunlight. So sometimes we put telescopes out in space so we can study things for longer periods of time, but we also can see a bit further if we get above the Earth's atmosphere. We don't have things like clouds in the way. And then as we go to longer and longer wavelengths, we can actually build telescopes for either the ground or for space. So one of the missions I'm going to talk about today is the James Webb Space Telescope, which operates at the infrared wavelengths. We also have other ones that go into the microwave region, such as WMAP. But then we can go to even longer wavelengths where we can actually use things like radio telescopes. There's radio telescopes all over the world. And the reason they're on the ground as opposed to space is, first of all, they have to be really, really big. So it's hard to get them into space. But also, we can actually see most of the radiation at radio wavelengths from the ground. So we don't have to go to space. So one of the most famous space telescopes is the Hubble Space Telescope. This telescope has been in operations for over 25 years now, which probably is almost as old or older than some of your parents even, which is quite fun to think about. The Hubble Space Telescope has rewritten our textbooks. It has basically given us a whole new insight into what space actually looks like. From things in our own solar system, we can really see with great sensitivity our planets and their moons. But we have even looked and learned a lot about things like how stars are forming, how galaxies are actually, how many galaxies we have, and probing things like how stars die. One really cool experiment that the Hubble Space Telescope did, though, was it looked at a blank part of the sky. So the person that operates the telescope said, I just want to stare at a dark spot in the sky where we didn't know anything existed. And when they did that, they stared for hundreds of hours. And when they processed the data, they came up with this image. This image is called the Hubble Ultra Deep Field. And basically, it's a very small postage stamp size. If you basically put your thumbnail up in the sky, that's how big it is. And within that image, we found thousands of new galaxies and new stars. This is something we never expected to see with the Hubble Space Telescope. And what we learned was we were just starting to barely see all of these things because the telescope just wasn't quite sensitive enough, or just on the edge of how sensitive it should be, in order to really study things that are really, really, really far away. So this actually motivated us to build an even more powerful telescope than the Hubble Space Telescope. And that's where we're coming with the James Webb Space Telescope. We needed something bigger, something more sensitive than even Hubble. This telescope has been designed so that not only can we see all these galaxies that the Hubble Space Telescope was able to, so here's the ultra deep field on the second line. This is showing you how far back towards the Big Bang we can actually see, and how far things are away from us is another way to think of it. So we were only able to see certain distances, and the longer and longer we stared, you can see that we could look even further. But Hubble just really didn't have the capability to go even further back into time towards the Big Bang, where the first stars and the first galaxies in the universe were actually forming. So that's where the James Webb Space Telescope was actually designed, and hopefully will help us probe this region. So we can go back just to the region right outside of the Big Bang, the time. If we want to think about time or the universe as like a human time scale, the Hubble telescope could see back to when the universe was about, let's say, in 5th grade or 6th grade. So maybe, you know, a young child or a child. The James Webb Space Telescope is actually going to be even look further back in time, where we're looking at the babies, the infants. So before you even started school, before you were even walking, that's what James Webb's going to really see for our universe. So a really, really, really long time ago. But it's also going to do other really amazing things. So one of the things the James Webb Space Telescope is really key to do is we can see at longer wavelengths. The Hubble Space Telescope is an optical telescope, so it sees just as you and I see. It sees colors. When we look in the sky, we see clouds, we can see trees, we can see the colors of the leaves as they're changing, but we can't see through things. We can't see through our clouds. We can't see through the Earth's atmosphere, especially during the daylight. So this is a picture that was taken of a cloud. Just as we have clouds here on Earth, we have clouds in space. This is where stars and new planets are actually being formed. But we can't really see through it because, again, the light's being blocked by a cloud. But if we go to longer wavelengths, which this image is going to transform, you can see that we can start really seeing all the stars and things behind this cloud that we couldn't see in the optical wavelengths. So this is an infrared image of the exact same cloud. So I'll go back. And if you watch it carefully, you'll see stars and things start appearing through all this gas and dust here in the middle. So this is what's really unique about having an infrared telescope. We can also do other cool things like study whenever a planet or one of its moons has a volcanic eruption. So we now know this happens on some of the satellites in our own solar system. So this is Europa. It's one of the larger moons of Jupiter. The Hubble Space Telescope actually saw gas coming out of Europa, suggesting that it has something spewing out, which is a volcano or whatever. So James Webb Space Telescope can tell us not only whenever that gas is coming out, but it can also tell us what that gas is made of. So is it really water? Is it lava-like? Or is it something completely different? So that's one of the capabilities that we have, is we can actually take our imager, which gives us a fingerprint across the entire planet, and we can see whether or not this gas is actually something relevant to what we would need for life. So the James Webb Space Telescope, so who is James Webb? He was our second administrator of NASA and a big advocate for actually doing science in space as opposed to only manned spaceflight. We have an extremely large telescope, and we're going to put that telescope 1 million miles away from Earth. So we won't be able to send astronauts there to fix it. The telescope's so big, actually, that we don't have a rocket big enough to launch it as a single mirror. So we have to fold the entire telescope up so we can get it into space. This is not only a NASA mission, it is also supported through the European Space Agency as well as the Canadian Space Agency. So it's a joint partnership, and it includes 15 countries around the world. And it's going to be operated the same way the Hubble Space Telescope is, up at a place near Baltimore, Maryland, called the Space Telescope Science Institute. This is what our telescope looks like. It's kind of funny looking. But as I said, we have a really big mirror. So this is 6.5 meters in diameter. So here is a picture showing you how big that is. This is an average man here on the left. So you could think of your father or another man in your life. And you can see, compared to the Hubble Space Telescope's mirror, that it's a little bit taller than an average man. But the James Webb Space Telescope actually stands on over 2 stories high. It is extremely tall. So you can see that we have a really, really, really big telescope, which is necessary to see all the sensitive things that we can't see with other wavelengths. We also have this funny looking boat thing on the bottom of our telescope. This is our sun shield. The sun shield's used to keep the telescope cold. Because we are looking at warmer things in space, we want to be sensitive to that. So we don't want the telescope to actually be warm. So we have this massive sun shield. It's about the size of a tennis court, or if you put James Webb down on a football field, you can see that we can fit about 5 of them going across the entire football field. So it's a really, really, really big telescope. So in order to get this into space, we have to fold everything up so it fits inside of a rocket. So this is what it looks like inside of our rocket, all folded up. And I'll show you a video in a second showing you how we actually unfold the telescope once it gets into space. So this is what it actually looks like. So we have it all folded up whenever we launch it in the rocket. The first thing we do is we give ourselves power. So we have a solar array. The solar array comes out, and then we have some communication satellites that actually start coming up. This is so we can actually talk to the telescope. These are the only 2 things that happen automatically. Every other thing you see from here on out is something we control from up here in Maryland. We tell the telescope when to do all of these major maneuvers. We actually have backups in case something fails. We can go in and we can re-trigger one of the mechanisms or try to make it work again. So we have a lot of control over what's actually going on. We have sensors all over the telescope telling us when things actually happened, if they were successful or not. Unfortunately, we don't have like a webcam, so we can't watch it actually happen. So these sensors are really important to us so that we know that things are happening in real time. So as you can see, we've now gotten to a phase where we've opened up our, tennis court size sun shield. Now we're going to start working on getting our mirror out so we have a nice big optical telescope. There's a lot of things that are happening that are sort of into the details of why we need them and what they actually are for. A lot of it are things that are helping us keep the telescope cold. So radiators, so they actually take the heat that actually happens from the electronics and the computers on board. We don't want any of that sitting on the telescope, so we have radiators that come out so that we can get away from all that heat. And that's what our telescope looks like, and it's going to sit 1,000,000 miles away from Earth. So with that, I'll happily answer questions. I hope you enjoy this, and hopefully we have enough time that you can let me know what you're thinking. And thanks so much.
Awesome, thank you, that was great. Now we can go around and do a few rounds of questions. So we can start with, let's start with Miss Otterber's class. So I can unmute you guys. And do you guys have a question you'd like to ask?
When's the James Webb Telescope going to be released?
So we're almost done building everything. We're doing a lot of testing right now, which we just finished a big test down in Houston, Texas. Once we verify that that test was successful, we're shipping the telescope over to California, where they're going to put the sun shield and the spacecraft on. Once that happens over the next year, we send it down to actually South America, where we're going to launch it on the rocket. And that's going to happen in the spring of 2019. So we have about 1.5 years, and then the telescope's going into space.
Exciting. All right, Miss Bodner's class, do you guys have a question that you'd like to ask? Let's see. Oh, there we go.
How did you find out how to make high-tech?
I didn't hear that question.
Yeah, can you repeat your question again?
How did you find out how to make high-tech?
Find out, and then I don't hear the rest.
I don't either.
Yeah, maybe come closer to the microphone. Or, yes, there you go.
How did you find out how to make these high-tech machines?
There we go.
We have hundreds of really smart engineers that work with the scientists to make our dreams come true. The scientists tell the engineers, we need a telescope that's so sensitive that we can detect the first stars in space. And we need to do it with this kind of spectroscopy. And then they go and they do a number of studies and calculations, and they come back and they tell us, okay, well, we need a telescope that's this big and it's sensitive on this level. So then we work together with the engineers and people that are developing different technologies. So we have to have really sensitive equipment and things like this. And we all work together and try to make what we really want to happen. This telescope was first drawn actually on a napkin in a restaurant in 1994. That was before a lot of you were born. So this telescope's been in progress and been being developed, and the engineers have been working really hard for a very long time.
Awesome. All right, so Miss Peterson's class, do you guys have a question you would like to ask?
Yep, 100%.
How does the James Webb Telescope see like back in time? Like the Big Bang?
Okay, so the way we see back in time, since we can't see with our own eyes that far across the universe or back in time. So what we do is we depend on looking at things. So by the time the light from the first stars and galaxies actually reach us, it slowed down significantly. That's because it has to travel a long time and a long ways. So we're talking billions and trillions of miles across the universe. So by the time that light actually reaches us, even though it's light just as you and I would see if it was here, it actually goes to longer and longer wavelengths. So the James Webb Space Telescope is optimized to look for these longer wavelengths because the light is actually slowed down just because it's been traveling so long and so far. So hopefully that answers your question.
All right. Now we'll go to Miss Krawitzki's class.
Okay. How long does it take to become a robotics engineer?
You're kind of cutting up.
Yeah, try it again. Say it one more time.
How long does it take you to become a robotics engineer?
To become a robotics engineer, that's a great question. You have to go through college. Sometimes you can just go straight through an engineering program, which it's a couple of years beyond what you would get besides a normal bachelor's degree in science, for example. But there's also different levels of engineers. So depending on you know, what level of an engineer, do you want to be a primary engineer that does all the main designs and you know, optimizes everything, or do you just want to be somebody that's putting something together and testing it? So depending on what level you really want to be at is where you'll actually have either more or less education. But regardless of your education, you still have to go through an apprenticeship and an internship, sort of a role. So you go and you work with other engineers and you can learn things real time and work with them, and they show you how the process works and how to do things. So it takes a little bit of time, but not quite as long as being a professional scientist, for example.
Awesome. So we can do another round of questions from everyone. So again, we'll start at the top with Miss Otterbury's class.
I want to do it.
How much money did it take to make the thing?
So we were really lucky because we have the European Space Agency and the Canadian Space Agency helping NASA. But the cost to NASA has been about $9 billion.
Whoa! Whoa!
That's a lot of money.
That's a lot of Legos.
Awesome question, guys. All right, Miss Bodner's class, do you have another question you would like to ask?
Oh, yeah. Oh, yeah, that's fine. Okay, and do we pick up the lunches in the office? Is that what you said? Oh, okay. All right. Thank you. Bye.
Oh, we have a question coming up.
How old were you when you started NASA?
How old was I when I started working at NASA? I was 26 years old.
Okay.
I should say I started working at NASA before I was actually hired at NASA. So I worked there for 2 years before I was actually hired as a full NASA scientist. So I was working there learning how to be a professional scientist after I got my PhD.
Is it difficult to get a job at NASA?
It can be. So the hardest part about getting a job at NASA is, first and foremost, you have to be a US citizen. We do hire some foreign people, but it's not routine. It's not easy to do as a foreign national. So we like to hire people to work for the government that are from our own country. But it also takes a lot of time and a lot of patience. So you have to be the best at your field in order to be considered for a job at NASA. So even if you're applying for something as simple as being an engineer that's tightening, you know, screws on a new spacecraft, or working in a laboratory doing analysis, you have to be really good, and people have to know that you're really good. So as a scientist, that means you have to publish a lot of papers, you have to give a lot of talks to not only schools and the community, but to other scientists all over the world. So it takes quite a bit of effort, but it is possible.
Awesome. All right, Ms. Peterson's class, do you have another question you would like to ask?
Can the James Webb Telescope see like to the end of a black hole?
Can it see to the end of a black hole?
Like
Yeah.
a black hole?
So what we can see is evidence of black holes. We don't really have the capability to see a black hole itself, because that's the reason they're called black holes, is they don't have any light. They absorb all the light. But what we can see is things like how a black hole affects the light around it. So whenever it's absorbing another galaxy or another star, we see how that's affecting those objects. And that's the kind of thing we'd use to study black holes at this day and age.
Awesome. And then our final question we'll have from Ms. Krowitsky's class.
How can the James Webb Telescope tell what the gases from space are made of?
That's a great question. So every gas that we know of, even ice or rocks, has a very distinct pattern that we look for. So just like I can tell the difference between you or your friend sitting next to you based on not only how you look, but also based on your fingerprints. So you know that we have different DNA, we have different fingerprints. We're looking for the fingerprints of different gases in space. So when we want to look for water, we look at the fingerprint of water. But if we want to look for something like methane, we look for the fingerprint of methane. And that's what spectroscopy actually does. It allows us to look for these fingerprints. So just because we can't actually see something in an image, it doesn't mean it's not there. So it's hard to see gas, right? So we are dependent on looking for the fingerprints of gas.
Awesome. All right, so that was our final question. So thank you everyone for joining us for our Google Hangouts on our last day of Space Week. And thank you, Stefanie, for coming and hanging out with us. We definitely all learned a lot. So I'll unmute everyone's mic and everyone can say a nice big goodbye and be live.
Thank you.